Have you ever wondered what the universe would look like if you could move faster than anything you have ever known? Imagine walking forward, only to realize that space, time, and even light itself begin to behave in ways that defy everything your senses have ever told you. As you approach the speed of light, the very fabric of reality begins to bend and twist. Time slows down, distances shrink, colors shift. What once seemed familiar becomes strange and surreal. But why does this happen? And what would it actually feel like to move at such incredible speed? In this video, we are going to explore that question by taking you on a journey, not just across space, but into the very nature of space and time itself. You will see how physics begins to behave differently the closer you get to the cosmic speed limit. From time dilation to warped vision, from visible infrared light to stretching shadows of the past, we will explore the transformation of your universe as your speed climbs higher and higher. Buckle in, because what you are about to see may forever change how you think about motion, light, and reality itself. Imagine if the speed of light was not a fixed constant, but something you could slow down, gradually, step by step, until it became no faster than your walking pace. What would the world around you look like? This is not just science fiction. The Massachusetts Institute of Technology created an interactive simulation to help us visualize this strange reality. In their game, A Slower Speed of Light, the player collects glowing orbs that do not increase their own speed, but instead reduce the speed at which light travels in the simulated world. This creates a rare opportunity to explore what everyday reality would feel like under the rules of Einstein's special relativity, without needing a spaceship. At the beginning of the simulation, everything looks normal. Buildings, trees, and the horizon appear just as they would in real life. But as the speed of light drops and you collect more orbs, something unexpected begins to happen. The colors around you shift, shadows grow longer, objects ahead begin to shimmer and distort. Your character is still walking at the same pace, but your experience of the world begins to unravel. What you are seeing is not a glitch in the graphics. It is a reflection of what physics predicts would actually occur if you could move at relativistic speeds, where space and time begin to act as one unified field. One of the first effects to appear is the shift in visible light. Colors change, sometimes dramatically. This happens because of the relativistic Doppler effect. As you walk forward in the simulation, light from objects ahead of you is compressed, its wavelength shortened. Infrared waves, normally invisible to the human eye, are pushed into the visible spectrum, allowing you to see heat as glowing reds or oranges. Ultraviolet radiation, once beyond your vision, appears as eerie purples and blues. At the same time, light from behind you is stretched out, fading into longer wavelengths. The world behind dims and loses color. It feels as if you are chasing light itself. Another remarkable phenomenon is the searchlight effect. Light from the direction you are moving appears to concentrate ahead of you. The intensity increases because more photons strike your eyes per second. Everything in front glows brighter, while everything behind seems to vanish into darkness. From a scientific standpoint, this matches what happens when a real object moves close to the speed of light. The photons that reach you are no longer evenly distributed. They are biased toward your direction of motion, collapsing your visible universe into a cone in front of you. The faster you move, the narrower and brighter that cone becomes. Perhaps the most surprising part of the simulation is that even though your walking speed remains constant, the world starts to behave as if you are moving faster and faster. Distances shrink. Your steps cover more ground than before. This is where time dilation begins to creep in. In the game, it is not your speed that changes, but the laws that govern space and time. Since light is now slower, time itself warps to maintain the constancy of physics. What you are seeing is a visual metaphor for what happens in the real universe at high velocity. As you continue to collect orbs and light slows further, you start to sense a break between your experience of time and the world's. By the end of the game, when the speed of light has slowed to a crawl, your perception of reality is fundamentally altered. Objects twist and blur. Your field of vision expands unnaturally, allowing you to see more of your surroundings at once. You begin to glimpse what is behind corners, not because your eyes are stronger, but because light is taking longer to arrive, revealing hidden angles as it bends around space and time. This is what relativity looks like when brought down to human scale. And while the game is a simulation, the physics behind it is very real. It is a powerful reminder that the speed of light is not just a number, it is the foundation upon which our reality is built. As your speed climbs closer to the speed of light, reality itself begins to shift. Not just in some abstract physical sense, but in the very way you see the world around you. If you were to travel at a significant fraction of light speed, the entire sky would seem to warp and bend. Shapes would distort, colors would melt into new hues, and your own sense of direction would become unreliable. These changes are not illusions. They are real, measurable effects that result from the very nature of light and time. The universe you once recognized would begin to collapse into something unrecognizable. One of the first and most dramatic changes is the transformation of color. Light, as you know it, travels in waves, and those waves are stretched or compressed depending on your motion. This phenomenon is known as the relativistic Doppler effect. As you move forward at near light speed, the wavelengths of light coming from in front of you are compressed. This causes objects to shift toward the blue and violet end of the spectrum. Meanwhile, everything behind you is redshifted, the wavelengths stretching so far they fade into invisibility. Your eyes begin to see what they were never meant to: infrared heat, ultraviolet patterns, even cosmic radiation. Another astonishing effect is called the searchlight effect. Because you are moving rapidly toward the photons in front of you, more of them strike your eyes in a shorter span of time. As a result, everything ahead appears brighter, more intense, almost glowing. It is as if a great cosmic torch has been lit in the direction of your travel, focusing the light of the universe into a narrow beam. Behind you, however, the opposite occurs. Fewer photons catch up to you, making the rear view darker and dimmer. Your visible world is no longer spherical. It has become a cone of brightness aimed forward through space-time. As your velocity increases further, space itself seems to squeeze. Objects in the direction of your travel appear flattened and condensed. This effect is known as Lorentz contraction. Imagine buildings or planets ahead of you being compressed along your line of motion, appearing thinner and closer than they truly are. It is not just a trick of perspective. It is a direct result of how space behaves when influenced by high velocity. At these speeds, distances are not what they were. From your frame of reference, everything ahead seems to rush toward you, collapsing into a rapidly approaching horizon. At the same time, your field of vision begins to change. Due to an effect called light aberration, your entire visual field is pulled forward. Stars that were once at your sides now crowd into your forward view. The universe behind you disappears, while the universe ahead seems to curve around into your face. It is as if you are no longer traveling through space, but pulling space itself toward you. The faster you go, the narrower your forward cone of vision becomes, until, at nearly light speed, it feels like you are staring down the barrel of existence itself. All these visual distortions remind us that light is not simply a background feature of the cosmos. It is the medium through which we experience everything, and that medium begins to change dramatically at high velocity. What you see is no longer what exists. It is what the universe allows you to see, shaped by your motion through it. As you drift closer and closer to light speed, you are not just moving faster, you are moving differently through space, through time, and through perception itself. Light becomes warped, and with it, reality bends. What if I told you that time does not flow at a universal rate? That your seconds are not the same as mine, and that speed itself can bend the passage of time? This is not fiction. It is a confirmed prediction of Einstein's special relativity. Time, once thought to be absolute, is actually relative, stretched and twisted by motion. As you move faster, especially approaching the speed of light, time begins to slow down. Not just for others watching you, but for you as well. And the closer you get to light speed, the more pronounced this effect becomes, until, at light speed itself, time halts completely. This phenomenon is known as time dilation. From your own perspective, everything feels normal. Your heart beats steadily, your thoughts move as always, and your clock ticks at its regular pace. But to someone watching you from a stationary point, your entire life appears to move in slow motion. A few minutes for you may span hours, even years for someone else. This is not a theory without proof. Scientists have tested it using high-speed jets, atomic clocks, and even satellites orbiting the Earth. Each time, the results confirm that time truly does slow down for moving objects. To visualize this, imagine two identical twins. One remains on Earth, while the other boards a spacecraft and travels near the speed of light. When the spacefaring twin returns, they will have aged far less than their sibling on Earth. This is not a trick or illusion. It is a direct consequence of their journey through space-time. The faster you move, the less you experience the passage of time. This is not just theory. It has been demonstrated in laboratories and in real-world experiments involving muons, particles that decay more slowly when accelerated to high speeds. In the simulation we explored earlier, your walking speed stayed the same, but the speed of light was reduced. Yet you seemed to cover more distance in less time. That is because, effectively, your time was running slower than the world around you. The game offered a visual metaphor for time dilation. In reality, high-speed travelers would not feel the effects themselves, but upon returning home, the discrepancy would become clear. This is one of the most profound aspects of special relativity. It reminds us that time is not fixed. It bends to motion, to velocity, and to perspective. And it is not just space travelers or subatomic particles that are affected. Even on Earth, tiny amounts of time dilation occur every day. The Global Positioning System, or GPS, must correct for time dilation caused by the speed of its satellites and the differences in gravity. Without accounting for these shifts, your GPS would drift several meters every single day. So yes, the bending of time is not just a cosmic mystery, it is part of the practical technology we use daily. Time, it turns out, is far more flexible than our intuition suggests. But perhaps the most mind-bending implication of time dilation is this. If you could somehow reach the speed of light, a feat impossible for anything with mass, then from your point of view, the entire universe would flash by in an instant. No time would pass for you at all. A journey to the edge of the galaxy would be over in a blink. From your perspective, the universe would collapse into a single frozen moment. And yet, for everyone else, millions of years would have passed. This asymmetry is not a flaw. It is a fundamental truth of our universe. And it reminds us that time, like space, is not absolute. It is dynamic, responsive, and deeply tied to how we move. Time is not just bent by speed, it is also bent by mass. Massive objects like stars, planets, and especially black holes do not just pull on space, they pull on time itself. According to Einstein's general theory of relativity, gravity is not really a force in the traditional sense. It is a distortion of the fabric of space-time. The more massive an object is, the deeper the dent it creates in this fabric. And in these dents, time does not pass the same way. It flows more slowly the closer you are to the source of gravity. The universe, it turns out, does not treat time equally everywhere. You might think this effect is only noticeable near extreme objects like black holes, but even here on Earth, it is measurable. Atomic clocks placed at the top of a mountain tick faster than those at sea level. That is because they are farther from the center of Earth's gravity well. The difference is tiny, just a few billionths of a second per year, but it is real. In fact, the global positioning system must account for both the speed of satellites and their position in Earth's gravitational field. Without correcting for time dilation caused by gravity, GPS devices would become useless within hours. The closer you get to a massive object, the slower your time flows. This becomes especially dramatic around the Sun. Mercury, the closest planet to the Sun, experiences a slightly slower passage of time compared to Earth. But near a neutron star or a black hole, the difference becomes extraordinary. A clock placed just above the surface of a neutron star would tick far more slowly than one in deep space. And near the event horizon of a black hole, the point of no return, time nearly comes to a halt. From the outside, it would look like you are frozen in place, suspended forever on the edge. This is not just theoretical. In 1959, physicists performed the Pound-Rebka experiment, shooting gamma rays from the top of a tower to the bottom and measuring how gravity affected their frequency. The results confirmed Einstein's predictions. The closer the radiation was to Earth's mass, the more compressed its waves became. This showed that time was indeed running more slowly lower in the gravitational field. Light itself felt the stretch of space-time. From this, we learned that time and gravity are not separate things. They are part of the same invisible architecture. What does this mean for us? In practical terms, we live our lives unaffected by these shifts. We do not feel time slow down, even if we are closer to the ground or orbiting in space. From our perspective, everything feels normal. But from a cosmic viewpoint, time is not fixed. It is elastic. Every step we take, every orbit we make, is shaped by the invisible warping of time. Gravity, that most ancient of forces, holds not only our bodies to the earth, but our very moments in place. And the deeper we fall into gravity's well, the more time itself begins to stretch and fade. Black holes are not just objects. They are edges, boundaries in our understanding of space, time, and reality itself. These immense structures are born from the collapse of massive stars, compressing matter into a region so dense that not even light can escape. But beyond their fearsome reputation lies something even more mysterious: the way black holes affect time. Near a black hole, time does not simply slow, it stretches, bends, and nearly stops. What we experience as seconds may become centuries to someone further away. This is not speculation. This is a consequence of gravity taken to its most extreme form. Imagine drifting toward a supermassive black hole, the kind found at the centers of galaxies. From your perspective, you are falling normally, time flowing just as it always has. But to an outside observer, something strange begins to happen. Your movement slows, your heartbeat, your breath, even the light escaping from your body. All of it becomes delayed, distorted. Eventually, as you approach the event horizon, it would appear to them that you have frozen in time. You would remain there, suspended forever, never quite crossing the threshold. And yet, from your own frame of reference, you would cross it in an instant. This is the profound and terrifying nature of the event horizon. It is not a surface you can touch. It is a boundary in space-time, a point beyond which the curvature of gravity becomes infinite. Once crossed, no information, no particle, and no light can return. But even before that moment, time is already being reshaped. This effect is known as gravitational time dilation, and around a black hole, it becomes so severe that time effectively stops for any external viewer. The deeper the gravity well, the slower the ticking of the cosmic clock. And the deeper you fall, the more space and time begin to change roles. In ordinary space, you are free to move through 3 dimensions of space and 1 of time. But inside a black hole, the roles reverse. Time becomes a one-way direction toward the singularity, a point where all matter is crushed into zero volume. You cannot avoid it, you cannot turn around, and you cannot choose a different path. It is as if the future has a gravitational pull, and the singularity is your destiny. The laws of physics, as we know them, break down here. Mathematics turns to infinity, and certainty dissolves into speculation. Some scientists believe that black holes may hold the key to understanding quantum gravity, a theory that unifies general relativity with quantum mechanics. Others have suggested that the singularity may not be the end, but rather a bridge, perhaps even a wormhole to another region of space or time. Yet all of this remains theoretical. For now, all we know is that black holes warp the universe in unimaginable ways. They stretch not only the fabric of space, but the very flow of time. Near them, you could watch the universe race forward, galaxies evolve, and stars die, all within what feels like moments. So, what are black holes truly? Are they cosmic destroyers, devouring all who come too close? Or are they windows into the deeper structure of reality, where time is no longer linear and space no longer behaves as it should? Perhaps they are both. What is certain is this: near a black hole, time itself reveals its flexibility. Seconds become centuries, movement becomes stillness, and the line between future and past begins to blur. It is a place where our understanding fails, and all that remains is gravity's overwhelming truth. What if time is not something that passes, but something we pass through? For centuries, humans have thought of time as a river, flowing steadily forward, carrying all things with it. But Einstein's theories shattered that picture. In the framework of relativity, time is not separate from space. It is woven together with it, forming a single four-dimensional fabric known as space-time. And if space can bend, twist, and stretch, then so can time. This is not just a metaphor. This is physics. Time is not merely a ticking clock. It is a direction, just like left or right, up or down. To understand this, imagine how we define space. In 3 dimensions, you can move forward and backward, left and right, up and down. These directions are independent of each other, and each one exists at right angles to the others. When we add time into this mix, we are adding a 4th axis, one that is also independent yet deeply connected to the others. It is not simply another number. It is a new kind of direction, one we move through constantly. Unlike space, we cannot choose to turn around and go backward in time, but that does not mean it is not there. From a geometric standpoint, treating time as a fourth dimension makes sense. If you look at a moving object, like a planet orbiting a star, its path through space over time can be represented as a continuous line in space-time, a world line. That line is not static. It is the record of every position the object occupies, from past to future. You too have a world line, one that began at your birth and extends into the future. Just like a three-dimensional shape has length, width, and depth, your existence stretches through time. In this sense, you are not just here, you are also when. Let us imagine for a moment what it would be like to live in a lower dimensional world. A two-dimensional being could only perceive surfaces, never height. A one-dimensional creature would live on a line, never aware of what lies beyond it. So, what about us? Could we, as three-dimensional creatures, be blind to higher dimensional realities? If time is just another spatial direction, albeit one we are limited to moving through in a single direction, then perhaps our view of reality is incomplete. Perhaps we are like flat drawings on a four-dimensional canvas, never seeing the shape we truly are. In this model, motion through time is just as real as motion through space. The faster you move through space, the slower you move through time. This is not poetic, it is measurable. The total speed through space-time remains constant for all objects. If you gain more velocity in space, you lose some in time. That is why time slows down at high speeds. It is as if you are tilting your motion away from the time axis. Imagine a ship sailing through the sea. If it turns toward the east, it moves less toward the north. The same is true for space-time. Motion in one direction comes at the cost of motion in another. When we visualize this idea, we can even represent ourselves as flat shapes along the time axis. In a way, your body is a three-dimensional cross-section of a four-dimensional object. You appear to change because you are slicing through different parts of yourself as you move through time. But the complete you, the you that exists across your entire life, is a long, thin, four-dimensional thread stretched across space-time. From the perspective of a being who could see all four dimensions at once, your past and future would be as visible as your front and back. What this model also suggests is deeply philosophical. If time is a dimension, then every moment in your life, past, present, and future, already exists in the fabric of space-time. You are not riding a train into an unknown future. You are the train, the tracks, and the journey all at once. This concept is sometimes called the block universe, where time does not pass, but all moments simply are. The illusion of time flowing is created by our limited perception, bound to a single moment at a time. In reality, the universe may be frozen, eternal, and complete. Of course, this view raises questions we cannot easily answer. If the future already exists, what becomes of free will? If time is simply a direction, why can we only move in one way? Is there a force that pushes us through time, like gravity pulls us through space? Or is time's arrow nothing more than entropy, the tendency for systems to move from order to disorder? Whatever the answer, the idea that time is a dimension like space challenges everything we thought we knew. It asks us to see ourselves not as points in time, but as beings stretched across it, threads of existence woven into the cosmic fabric of everything. If time truly is a dimension, then what does it mean to move through it? And more importantly, can we think of time as a direction in the same way we think of left or right, forward or backward? In the framework of special relativity, every object moves through space-time at a constant speed, specifically the speed of light. This does not mean we are flying through space at that speed. Instead, it means that our combined motion through space and time always adds up to the same total. If we move faster through space, we must slow down through time. Time is not just a ticking clock. It is a direction we move through, a component of our four-dimensional motion. Imagine a vector, a single arrow, representing your motion through the universe. If you are at rest in space, your entire vector points along the time axis. You are not moving through space, but you are moving fully through time. Now, imagine beginning to walk, then run, then travel in a spacecraft. As your velocity in space increases, your motion vector begins to tilt. It still moves forward through space-time, but now some of that motion is allocated to space, and less is left for time. This tilt is what causes time dilation. You are no longer traveling as quickly through time as you once were. This model helps us understand the relationship between speed and the passage of time. You cannot gain more motion in space without giving something up in time. It is like being on a river with a fixed current. If you turn your boat sideways to reach the shore, you move slower downstream. The universe behaves similarly. You always move through space-time at the same overall rate, but you can choose how much of that motion is spent on space and how much on time. When you move faster through space, your time slows down relative to observers at rest. This is not a distortion, it is geometry. This vector-based view of time also explains why light, which has no mass, does not experience time at all. A photon moves entirely through space. Its vector lies completely along the spatial axis, with none remaining for time. From the photon's perspective, which is a tricky phrase since it does not truly have one, its entire journey happens in zero time. It is emitted, travels across the universe, and is absorbed, all in the same instant. Meanwhile, for us, that same journey may take years or centuries. This is the power of motion's orientation through space-time. The same path appears differently depending on how your vector is angled. In this way, we can think of the passage of time not as a universal experience, but as a result of how we are angled through the universe. Time is not merely something that happens to us. It is something we move through, shaped by our motion, bent by our velocity. Just as turning your body changes your direction in space, accelerating your motion changes your direction in space-time. This is the quiet, elegant truth at the heart of relativity. Time is not separate from space. It is not static. It is a direction, and how we move through it defines everything we are. There is an experiment so famous in physics that it has become almost mythical: the double slit. At first glance, it seems simple. Shine a beam of light at a screen with two narrow openings and observe what appears on a wall behind it. If light behaved purely like particles, you would expect two distinct bright bands, one for each slit. But that is not what happens. Instead, you get an interference pattern, a series of light and dark bands, as if waves are overlapping. The light has interfered with itself. It has gone through both slits at once, and with that, everything we thought we knew about particles begins to unravel. The mystery deepens when you try to observe which slit the photon actually passed through. The moment you measure its path, the interference disappears. Now the light behaves like a particle again, choosing a single slit. Somehow, the act of observation collapses its wave-like nature. It is as if the light knows it is being watched. This strange duality, wave when unobserved, particle when measured, lies at the heart of quantum mechanics. But what if this bizarre behavior could be extended, not just in space, but in time itself? In recent years, scientists have constructed what they call a time slit. Instead of placing two openings in space, they created two openings in time. Using a special material that could be switched between transparent and reflective in a matter of femtoseconds, they allowed a laser pulse to interact with the material at two different moments. The result? An interference pattern, not in position, but in frequency. In other words, the light wave did not interfere in space, but across time. Light was not just in two places at once, it was in two times at once. Reality had bent in a direction we do not usually consider. What this suggests is astonishing. Time, like space, may be something that quantum particles can traverse in ways we do not fully understand. In the same way a photon can explore both slits before choosing a path, it may also explore different moments before finalizing when it actually existed. The interference in the time slit experiment implies that the photon did not merely arrive. It sampled multiple timelines, interfering with versions of itself separated not by distance, but by duration. This is not just odd, it is deeply unsettling. It suggests that even time might be non-local and probabilistic. This brings us back to a fundamental question. What is time? In classical physics, time is a straight line. It flows in one direction, forward, from past to future. But in quantum mechanics, that clarity dissolves. Events do not always have clear causes. Measurements influence outcomes that seem to reach backward. In the time slit experiment, the present state of a system appears to interfere with both its past and future. Light does not just travel through time, it dances through it, sampling possibilities and collapsing into a moment only when required. What does this mean for us? It means that the universe may be stranger than we imagined. Time may not be a river. It may be a vast field, one that we cross in a straight line only because we do not know how to move any other way. But light, in its strange and rebellious nature, might already be doing so. In bending around the laws of space, and now even time, it shows us a universe not ruled by certainty, but by probability. And within that probability lies a deeper truth. Reality, as we perceive it, may be only a small part of what truly exists. Time is not what we think. It never was. From the moment we are born, we are taught that time moves in one direction, forward. First the cause, then the effect. First the match is struck, then the flame appears. This is the principle of causality, the backbone of logic, and one of the most sacred assumptions in science. Without it, nothing makes sense. Predictions collapse, explanations unravel. But in the strange and uncertain world of quantum physics, causality may not be as safe as we once thought. There are experiments, real, repeated, peer-reviewed experiments that suggest something extraordinary. Information might be traveling backward through time. One of the clearest examples comes from quantum entanglement. Take two particles that are born together in a shared quantum state. They are then separated by vast distances, yet somehow remain connected. Measure one, and the other instantly responds, no matter how far apart they are. It is as if the universe violates its own speed limit. No signal, not even light, is supposed to travel faster than the speed of light. Yet this connection seems instantaneous. How does the second particle know what happened to the first? One explanation is that some kind of influence has traveled backward in time, an echo of the future rewriting the past. The delayed choice quantum eraser experiment pushes this even further. In this experiment, a photon passes through a double slit, forming an interference pattern, unless we later decide to observe its path. And here is the twist. The decision to observe or not can be made after the photon has already passed through the slits. Yet the photon appears to behave differently depending on what we choose, after the fact. It is as if the future decision changes the past event, as if the photon somehow knows what we will decide and adjusts its behavior to match. In this setup, the timeline seems to fold, with cause and effect slipping out of order. To preserve causality, physicists have offered several explanations. Some suggest that the wave function never truly collapses, and what we see is merely our limited view of a deeper, probabilistic reality. Others propose retrocausality, a model in which events in the future influence the past in subtle, non-paradoxical ways. These ideas are controversial, but they are gaining traction. The mathematics allows it. The experiments support it. The deeper we dive into the quantum realm, the less certain we become that time flows only forward, and the more we wonder if particles exist outside the river of time altogether. The notion of retrocausality is unsettling. It threatens the linear structure of time we rely on. But it does not necessarily create paradoxes. In most interpretations, the future does not change the past. It completes it. The influence works both ways, like a handshake across time. Events are not pushed by the past or pulled by the future, but resolved together in a web of correlations. The photon does not choose a path because of our future action. It becomes part of a complete timeline where all pieces fit, a tapestry already woven, only now being revealed, thread by thread. This leads us to a broader question. What if causality is not fundamental at all? What if it is an emergent property, something that arises from deeper laws we do not yet understand? In classical mechanics, cause and effect are clean, rigid, absolute. But in quantum mechanics, they dissolve into probabilities and entanglements. Perhaps causality, like temperature or pressure, is a macroscopic illusion, something that works well on large scales, but loses meaning at the level of individual particles. If so, then time travel, not the science fiction kind, but the informational kind, may already be happening right under our noses. So, is physics breaking causality? Maybe not. Maybe causality was never absolute to begin with. What we are witnessing may not be a violation of logic, but a reshaping of it. The universe is not a one-way street. It is a four-dimensional landscape. And from the right perspective, perhaps cause and effect are not chained in a line, but coexisting across time. Past and future, observer and observed, action and result. They may all be part of a single quantum whole. One that defies intuition, but not reason. One that challenges our minds, but not the mathematics. And that, in itself, is a new kind of order. There is a phenomenon in quantum physics so strange, so counterintuitive, that even Einstein famously called it spooky action at a distance. That phenomenon is quantum entanglement. Two particles become linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are in space. Measure one, and the other reacts, immediately, not quickly, instantly. Faster than any signal could travel, faster than the speed of light. And perhaps, if we look closely enough, faster than time itself should allow. To see why this is so disturbing, consider the idea of locality. In classical physics, objects influence one another through direct contact or through fields that propagate through space over time. Entanglement shatters that framework. When two particles are entangled, their properties are not separate. They are part of a single shared system. Measure one, and the other instantly aligns, regardless of distance. From one perspective, it is as if information has leapt across space with no delay. But from another, something even more unsettling may be happening. That information is also crossing time. Some interpretations suggest that the instant connection between entangled particles is not bound by time at all. That when you measure one particle, it is not just affecting the other in space, but also in time, collapsing histories, aligning futures. The entangled state exists outside of linear time. The particles are not exchanging messages. They are part of a single whole, and that wholeness stretches across temporal boundaries. In that view, the measurement does not cause a change. It simply reveals a timeless relationship that was always there, waiting to be unveiled. Experimental setups have tried to break this entanglement by separating the particles by great distances, by moving detectors, by introducing time delays. Yet the results are always the same. Correlations remain perfect. Even when the choice of measurement is made after the other particle should have been detected, the symmetry persists. It is as if the universe is not calculating events in order, but all at once. From our point of view, it seems like the future is changing the past. But perhaps it is more accurate to say that both are entangled in something deeper, something beyond time. This leads to the possibility that quantum entanglement is not just spatial, but temporal. That it connects particles not only across distance, but across time. Some physicists now speak of entangled histories, in which events that happen at different times are linked in ways we do not yet understand. It may be that entanglement binds not just what is, but what was and what will be. That by measuring one system today, you are influencing the state of another system that existed yesterday, or will exist tomorrow. In such a universe, information is not sent or received. It simply exists, woven into the fabric of reality itself. If this is true, then our entire understanding of time, cause, and information must be rewritten. Perhaps the future is not a blank page, but a mirror, reflecting the choices we have already made, or will make. Perhaps memory and prediction are just shadows of entangled outcomes. And perhaps the cosmos is not made of particles and waves, but of correlations, relationships so deep that they are immune to space, immune to time, and perhaps immune to death itself. In the realm of quantum entanglement, we are not separate from the universe. We are connected across every axis, every instant, every possibility. What if the past was not as fixed as we thought? What if the decisions we make in the present could somehow ripple backward and shape events that have already happened? This may sound like science fiction or a paradox from a time travel movie, but in the world of quantum physics, it is a very real question. And at the center of it stands one of the most mind-bending experiments in modern science, the delayed choice experiment. Designed to challenge our understanding of observation, causality, and time itself. This experiment asks, can the act of measurement now change what a particle did in the past? The roots of this experiment go back to the classic double-slit setup, where photons or particles pass through two slits and create an interference pattern, as if they behaved like waves and pass through both slits simultaneously. But when we observe which slit the particle went through, the interference vanishes. The particle chooses a single path. Observation appears to define reality. But what happens when we delay that observation? What if we wait until after the particle has already passed through the slits before deciding whether or not to observe? This is exactly what the delayed choice experiment does. In this setup, the decision to insert or remove a detector is made after the photon has already entered the apparatus, after, in theory, it should have chosen a path. But the results are astonishing. When the detector is inserted after the photon has passed through the slits, the interference pattern disappears, just as if the photon had gone through only one slit. When the detector is not inserted, the interference returns, as if the photon passed through both. It is as though the photon waits until the future is decided before committing to its past. The implications are staggering. Somehow, the photon seems to know what you are going to do and adjusts its behavior accordingly. Or perhaps more accurately, the act of measurement does not just affect what we see, it affects what was. This is not merely about detecting a path, it is about rewriting history. And yet, no signals are traveling backward in time. No laws are being broken. What changes is our understanding of what the past truly is. Maybe the past is not a fixed sequence of events, but a cloud of possibilities, waiting to be crystallized by choices made now. One interpretation is that until a measurement is made, the photon does not have a history. It is not that the past is being altered. It is that the past did not exist in a meaningful way until the present gave it shape. In this view, time is not a line, but a loop of dependencies, where the present and past exist in a kind of mutual agreement. This idea, though radical, is supported by the math of quantum mechanics. The wave function does not care about when a measurement is made. It simply collapses into reality whenever and wherever an observer steps in. The delayed choice. Quantum erasure pushes this concept even further. In some versions of the experiment, entangled particles are used, and the decision to erase or preserve which path information is made even after the detection of the particle. The interference pattern, or lack thereof, appears retroactively. It is as if the future measurement reaches backward, editing what the particle seemed to do earlier. These experiments do not just challenge causality, they defy our intuition of what time is and what reality is made of. So, can the future change the past? According to classical physics, absolutely not. But quantum mechanics is not classical. It is a theory where cause and effect blur, where particles can exist in many states at once, and where time seems less like a river and more like a tangled web. Perhaps our choices do not just shape our future, they reach backward and give form to the past. Perhaps what we call history is not set in stone, but carved in layers by the knife of observation, one moment at a time. After this long journey through photons and paradoxes, entanglements and delayed choices, we are left with a question more profound than any equation can answer. What do we truly know about time and light? We began with simple questions. What happens as we move faster? What does light see? How does gravity bend time? But the answers have revealed a universe more mysterious than we imagined. Time, we discovered, is not fixed. It bends, it slows, it may even vanish entirely. And light, though silent and massless, carries with it the power to shape what we see, when we see it, and perhaps even what is real. Time is no longer just a backdrop to events. It is a dimension we move through, shaped by speed and gravity, by mass and motion. It stretches near black holes. It halts for photons. It dances with causality at the quantum level. What we call now is not the same everywhere. What we call past might not be fully settled. And the future, well, the future may be participating in this story more directly than we ever dared to believe. Our experience of time is personal, local, and fragile. It is not the universal clock we once thought it was, but a thread we carry through a much larger tapestry. And then there is light, the silent messenger, the speed limit of the universe, a wave and a particle, a ghost that does not experience time, yet defines our perception of it. Light reveals the distant past, showing us galaxies as they were millions or billions of years ago. It shapes our measurements, our understanding, and even our reality. Yet, in experiments, light defies expectation. It goes through two slits at once. It waits for our decision. It seems to know the difference between being watched and being left alone. It is obedient to the laws of physics, and yet those laws feel bent around it. So, what do we know? We know that the deeper we look, the more questions we find. That light and time are not simple components of our universe, but windows into its deepest structure. That our models, while brilliant, are just that, models. They reflect the world, but they are not the world. Behind every experiment is a mystery that remains. And perhaps that is the greatest discovery of all. That the more we understand time and light, the more we realize how little we truly know, and how much more there still is to explore. In the end, light is not just what lets us see, it is what lets us ask. And time is not just what passes, it is what frames every question we ask it within. Between the two, we find ourselves, curious beings, flickering briefly in a vast and ancient universe, wondering not only what we are seeing, but when. And perhaps that wonder, more than the answers, is what truly makes us human. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.